In the last lecture, I was discussing about the multifunctional epoxy resin as matrix resin for composites. I discussed about a combination of epoxy and phenolic. From the phenolic resin, from the suitability point of view, here the Novolac grade resin was used from Novolac grade phenolic resin was used with epoxy. Now, this combination gives a very good curing characteristics, curing properties, cross-link density, leading to stronger composites. Now, this Novolac resin, phenol formaldehyde resin, that gives a thermal stability, heat resistance, etc., and this epoxy contributes to toughness. So, toughness, strength, thermal stability, these properties are combined in a composite made from epoxy resin and phenol formaldehyde resin in the form of Novolac. Now, there can be other multifunctional epoxy resin. Increasing the functionality means that will lead to have higher cross link density. Now, if you look into this molecule, this is diamino diphenyl methane. This diamino diphenyl methane was reacted with 1 mole of diamino diphenyl methane was reacted with 4 mole of epichlorohydrin, having this nitrogen as trifunctional, So, it combines with this nitrogen combines with this aromatic moiety, and this is epoxy groups. So, 4 epoxy groups are combined to this molecule. So, when this is polymerized, that leads to huge cross link density, and it contains this CH2 linkage, CH linkage, all these things, as well as here CH2 linkage and aromatic linkage and oxygen, these are terms. So, this gives a combination of very strong and tough as well as thermally stable composite. So, this can be a good characteristic of multifunctional epoxy resin, and this TGDMA is formed from the reaction of methylene dianiline. You can say this as methylene dianiline or diamino diphenyl methane with epichlorohydrin. As I told, this resin is preferred for high temperature aerospace application. So, you can say this kind of multifunctional epoxy resins are used for high performance applications in aerospace industries, in aircraft, for aircraft application. Now, let us look into the phenolic resin. We are discussing about the epoxy resins, epoxy resin, Novolac phenol formaldehyde combination. Now, let us look into phenolic resin. What is this phenolic resin? Now, this phenolic resin is an age old resin. Actually, this phenolic resin found the commercial scenario when Dr. Birkeland he discovered this bakelite. He developed this bakelite, that was the first thermoset resin and first composites or bakelite phenol formaldehyde composites developed by Dr. Birkeland, and from his name this bakelite was given to this kind of product. Till date there is continuous research going on with this phenol and formaldehyde condensation product. What is the reason behind this? This is a very good matrix regime till today, unbeatable system one can say. Now, this phenol, the formula of phenol is this. It has got 3 functional sites, 2 ortho and 1 para. These are reactive. Now, when it reacts with formaldehyde, basically formaldehyde is written in this form HCHO, we can formaldehyde, this formaldehyde available in the form of formalin, it gives basically methylene glycol. Formaldehyde with water, it forms methylene glycol. This methylene glycol reacts with phenol, that means formaldehyde reacts with phenol in the form of methylene glycol, forming this kind of product. This is known as trimethylol phenol. You see, this trimethylol phenol, it has got 3 functional reactive functional groups. When this trimethylol phenol further reacts with this phenol and formaldehyde, say gradually this chain increases, chain length increases, go on increasing, CH2 it can link up with another phenol unit, this way it continues. Now, this chemistry is a complicated chemistry dealing with 3 different reactive functional sites. Now, one thing here it can be explained that while phenol, formaldehyde, these are present, whether it will grow in this direction or in this direction, because this is also reactive, this can also react with another phenol, this can also react with another phenol. So, in all these directions, this direction, this direction, this direction, it can react. Ultimately, it can grow and it can form a product, high viscous as well as gel like 3-dimensional network product. But in order to make in order to have this suitable fabrication and processing facilities, it should not gel or cross link during the before the final fabrication, final shaping. For that reason, it must be controlled, the reaction must be controlled. Now, there are 2 different catalysts here, you see there are 2 different catalysts. There is one acid catalyst H plus and the another is OH minus alkali catalyst. So, phenol and formaldehyde can condense in acid catalyzed medium as well as in base catalyzed medium. When it reacts in presence of acid catalyst, the ratio of the phenol to formaldehyde is different than that of the base catalyzed reaction. Here in case of acid catalyzed reaction, ratio of phenol to formaldehyde is 1 is to less than 1 mole of formaldehyde. Now, this formaldehyde can be considered as a condensing agent as well as a cross linker for this kind of resin system. Here, if this the quantity of this formaldehyde is kept less, say 1 mole react with less than 1 mole of this formaldehyde, the resin formed that will be in the available in the form of linear molecule, which will remain as thermoplastic, and that grade is known as Novolac resin. Now, this Novolac resin will not cross link itself. To make it cross linkable or to cross link this Novolac resin, another cross linking agent known as hexamethylene tetramine, its formula is little complicated here. Hexamethylene tetramine known as hexa technically, this hexa decomposes to form amine and formaldehyde. This amine and formaldehyde basically becomes the reactive cross linking agent with this Novolac resin to form a 3-dimensional network. In case of bakelite switchboards, switches, sockets etc., or electrical that insulators, in those cases this Novolac resin was used mixed with wood flour along with hexa, and after compression, during compression molding under heat and pressure, that converts this Novolac resin to a thermoset bakelite resin for PF for phenol formaldehyde resin product. Now, in case of Resol, here this formaldehyde in the form of formalin, formalin basically solution of formaldehyde, say 40% 37% solution of formaldehyde in water. When it remains soluble in water, that is represented as methylene glycol, as I told just few minutes back. This CH2O is this methylene glycol. This is formed from formaldehyde and water. So, this is a water based system, This water based system in presence of alkali can form Resol resin when the ratio of formaldehyde or amount of formaldehyde is more than 1 mole of this phenol. Here you see, if you compare these two different structures, here the para position some growth is there, para position some reactive group is here, whereas in this case this para position remains free, which will be used up during cross linking, but here these are also formed by virtue of the higher amount of formaldehyde over here, and this remains this resin remains liquid, water based resin, a liquid resin. In this case, during the condensation reaction, this also this proceeds in water medium, but after certain growth of certain molecular weight, this separates into a different phase, organic phase, and there will be separation of water and organic phase. In the organic phase, this resin will be there, in the water phase other things will remain, and this organic phase will be taken out, and on cooling it becomes a brittle solid, and these reactions are carried out at around 80 to 90 degrees Celsius temperature for more than 1 hour time. So, this is a little in brief the chemistry of this phenolic resin, which is a good thermoset matrix resin for making composites. Now, again another kind of condensation polymer is polyimide. Now, polyimides are high performance resins, one can say engineering polymers, engineering thermoplastics, and that can lead to high performance composites. Now, these polyimides are made from dianhydrides. Say typical example is this is known as pyromellitic dianhydride. This is one anhydride, this is another anhydride. So, this is called dianhydride. Anhydride means it is in dry condition, it forms this anhydride ring. In contact with moisture or water, this anhydride ring will open up, forming carboxyl groups. That means, you can say this can be tetracarboxylic acid. Basically, it is a tetrafunctional compound. In this formula, this Ar here is this phenyl ring. So, basically, this compound and this compound are same. This compound and this compound are same. So, one can take dianhydride or diester acid. That means, here aromatic ring is there. So, one carboxyl group here in this case can be in the form of two carboxyl group in the form of ester group. Say in place of H, if we write R some alkyl group, this is an ester and these two acid groups. So, these two are the precursor, these two are the starting raw material, material for making polyimide. Now, this such type of compounds react highly with this diamine. Now, this diamine for this high performance resin, basically they are aromatic diamine. That means, there can be some aromatic ring, one or more than one aromatic ring. So, this is phenylene diamine, or one can have diamino diphenyl methane. This kind of diamine. So, this dianhydride or diester acid reacts with diamine in aprotic solvent like say N-methyl pyrrolidone, dimethyl formamide or dimethyl acetamide. So, these compounds are dissolved in this solvent and heated. On heating, what happens? This amino group react with this acid group, these acid groups or this anhydride group forming this opening the anhydride ring reacts with this amine group forming amide linkage CONH NH. So, this is known as polyamic acid. Now, this polyamic acid, it is further reactive, having this NH functional group. This NH functional group can react with this carboxyl group, can form a ring when it is heated at high temperature. Gradually it is heated from say ambient to or say 150 degree Celsius to 300 degree Celsius temperature in dry condition, it forms a ring. This is called imide ring. Here you see this amide linkage is converted to imide link by reacting with this carboxyl group, this imide ring. So, basically it forms a double strand polymer or multi strand polymer or ladder polymer which looks like this, ladder like structure. How? Say if we write the formula, it continues this way like this side also. So, you see this basically the backbone of this polymer molecule is rigid, having this ring configuration, imide ring, phenyl ring, imide ring, phenyl ring, imide ring, phenyl ring. So, we can consider this molecule like this. So, this line resembles this dotted line, this line resembles this line resembles this dotted line, and these linkages are the steps of the ladder known as double strand, or you can say multi strand polymer. So, this is highly thermally stable or thermostable polymer, and once this structure is formed, it becomes insoluble and infusible. So, these polymers can be very high performance polymers, and in high temperature applications, in aerospace applications, in aircraft applications, or in spacecrafts, these polymers are used for making composites with again high performance strong fibers, say carbon fibers or aramid fibers. So, this polymer is known as polyimide, and this polyimide is formed out of condensation of dianhydrides and diamines. Now, one thing I should mention at this point of time, now in this polyamic acid stage, it is soluble in solvent. So, the product is to be fabricated, say if somebody wants to make composite, the composite is to be fabricated at this polyamic acid stage, which remains in a solution in a solvent. So, this solvent of polyamic acid should be used for soaking a fabric, then that polyamic acid soaked fabric or ply or layer can be heated at elevated temperatures from say 100 to through 150, in stepwise the temperature is to be increased, then up to at 300 degree it completes the imidization, this ring imide ring formation becomes complete. Once this imide ring formation is complete, it becomes insoluble and infusible. Although initially, so at this point of time I should mention that although initially at the till the polyamic acid stage this polymer remains thermoplastic, but once this imide ring is formed it becomes thermoset, and by that time it has already been covered, this polymer has already covered the fiber in the composite. So, that and also it gives a very good bonding with the fiber, this matrix resin gives a very good interface bonding with the fiber surface. So, if a high aspect ratio fiber is used as the reinforcement, and this polyamide is used as the matrix resin, one can obtain a very high performance, thermally stable and strong composite. There can be other category of polyamides known as addition polyamide. Addition polyamide in the sense, as you have seen in the previous case, that imide means that must have imide linkage like this. Okay. Now, that the property of flexibility, mechanical properties, shock absorption, toughness, all these things can be controlled or tailored if we tailor this part of the polyamide resin. Here you can have one rigid phenyl ring or you can have a flexible linkage, like in this structure you see here CO group is there, or one can have some ether linkage in place of CO, one can have ether, only oxygen over here. Now, this particular polyamide was made from diamino diphenyl methane and benzophenone tetracarboxylic dianhydride. Say diamino diphenyl amine DADPA or DADPM, which one is convenient, you can say diamino diphenyl methane, it will be DADPM, diamino diphenyl methane, DADPM plus BTDA. BTDA is benzophenone tetracarboxylic dianhydride. This DADPM and benzophenone tetracarboxylic dianhydride, this is the benzophenone tetracarboxylic. This tetracarboxylic means it originated from one carboxyl group, it originated from another carboxyl group, another carboxyl group, another carboxyl group. So, 4 carboxyl group. So, this is benzophenone tetracarboxylic dianhydride that was reacted with diamino diphenyl methane. So, this amino group, this nitrogen is from amino group, and that amino group reacted with this dianhydride group forming imide linkage. So, here you see methylene linkage is there, CO linkage is there, that imparts some flexibility to this polyamide. This is also a polyamide and this is also another polyamide, but their properties are different. Properties of this polyamide is different from the properties of this polyamide. Apart from this flexibility, this polymer can be further kept in the reactive form known as addition polyamide. You see the N groups are reactive groups, that is actually formed from the bismaleimide moiety, bismaleimide moiety. Having this double bond over here, this system becomes reactive. Look into this here. This API addition polyamide is a reactive system and that is curable or cross linkable. So, that cross linking or curing of that addition polyamide occurs via this reaction. So, this curing of the addition polyamide occurs at elevated temperature, say around 275 degrees Celsius, by the combined addition reaction of the maleimide N group. This is the maleimide N group, malic imide. Maleimide means malic anhydride, this is the malic anhydride imide. Malic anhydride when reacted with amine, it forms maleimide, this maleimide. This maleimide N group is there in the polymer. Okay. So, this maleimide combined by the addition reaction of the maleimide N group and the cyclopentadienyl group, which was generated by reverse Diels-Alder reaction from this N group of this polymer. Once again I am going back to this thing, sorry, this N group, these are the N groups. These N groups actually these N groups breaks into maleimide and cyclopentadienyl group. Now, these two groups, once it is formed from the N groups of that addition polyimide, that help in undergoing cross linking reaction in this form. This is the rest part of the polymer chain, So, this is one direction of the polymer chain and this is another direction of the polymer chain, which can be linked up with another polymer molecule. So, it forms a cross linked configuration. So, that is generated by a reverse Diels-Alder reaction. So, these two are formed by reverse Diels-Alder reaction. When they combine to form this kind of thing, that is known as the Diels-Alder reaction. In this direction it is called reverse Diels-Alder reaction. Other examples of other addition polyamides are again this can be a benzophenone tetracarboxylic dianhydride type of molecule or compound having, it is not anhydride, but it is a derivative of that anhydride. These are the two ester groups, diesters and diacid. Having a molecule having two diester and diacid. So, all of them can react with diamine, aromatic diamine or aliphatic diamine in presence of this molecule having this cyclopentadienyl group. Okay. Or actually basically this is ethylidene norbornene type of structure. So, having this carboxyl and ester group that forms this kind of polyamic acid. Again this is polyamic acid. This polyamic acid having this group, then this polyamic acid will lead to imide ring formation. Okay. Here also one group is missing over here. So, that can also form the imide ring, it is missing here. This similar carboxyl group can be will be there in this at this position. So, this will form one imide ring, this will form another imide ring, and these reactive N groups are there as before. It will be cross linkable as well as polyimide structure will be formed, and at the same time this flexible linkage is there. So, toughness, stiffness, strength, thermal stability, all these things are tailored in the form of thermoplastic or thermoset configurations to have a broad spectrum properties of this kind of matrix resin for high performance, for making high performance composites. Now, the previous two cases, formation of polyimides that involves organic solvents, those are basically high profile, one can say high boiling solvents having very strong solution power. Ordinary solvents cannot dissolve such polyamic acids, but involving solvents for making composites, that is not a good approach from the point of view of this environmental pollution. So, if a process of composite preparation is without using any solvent or solventless, then that is most acceptable in industry. So, people tried without using any solvent, that means they took the reactant and on heating, if those reactants can melt and if such chemical reactions can occur in melt condition, that is highly welcome. So, there is solventless aromatic polyimide, addition polyimides without using any solvent, they are known as melt processable. So, here you see as before these are the carboxylic or anhydride or multifunctional aromatic acids, you can say. These are the amines, acids and amines having ether linkages, having phenyl rings, and again another system having acetylene group at the ends, acetylene and amine group. This amine group can react with these carboxyl groups or ester groups, and acetylene groups remains at the end. So, inside the molecule there can be imide linkage, there can be ether linkage, there are phenyl rings. So, that contributes to the rigidity, thermal stability, flexibility, toughness, all those will be tailored by the presence of such groups and moieties, whereas at the end group there are acetylene groups are present, which will help in curing of the resin. So, ultimately from thermoset system it can lead to a thermoplastic system, it can lead to a thermoset system, although having such phenyl ring and ether linkage, flexible as well as rigid system inside. So, that leading to the thermal stability of the polymers. Bis-maleimide, malic anhydride imide, maleimide resins. Now, this is a diamine. Again here X means X can be either methylene, can be sulfone, can be ether. That is, if there is CH2 it will be diamino diphenyl methane. If there is SO2 in place of X, that will be diamino diphenyl sulfone. If there is oxygen, that can be diamino diphenyl ether. If there is such groups, then it will be again a different diamine. So, all those possibilities are there in diamine part of the reactants. Then take the malic anhydride, this is malic anhydride. This malic anhydride in dry condition that can react with this amine group in melt condensation reaction, forming this polyimide. Okay. And having these imide malic anhydride, malic imide group at the as the end groups, which are reactive. So, inside there can be this phenyl ring, flexible units, imide linkage, all these things, but at the end group there will be some reactive. So, ultimately that compound that polymer can be curable also. So, these bis-maleimides are addition polyamides developed due to good drape and tack and the epoxy like cure conditions due to the presence of these maleimide groups, that they are able to offer in realizing better high temperature performance. Say service performance can be between 175 to 230 degrees Celsius versus epoxy resin, which perform little lower at the little lower range 120 to 175. So, if somebody wants to use a composite beyond 175 degree Celsius temperature, so that epoxy composite will not be suitable. In that case, one has to use this type of bis-maleimide resin composite or polyimide or the other addition polyimide composites, which can stand beyond 175 degree Celsius temperature for a prolonged exposure. Other examples, cyanide esters are also cyanide esters forming these ocean groups, cyanide esters can be formed. The formula is like this. And polyaryl ethers, polyaryl ether polyaryl ether sulfone, you see this is diamino, this is actually sulfonyl diphenyl sulfone, sulfonyl chloride. I have some doubt about the nomenclature of this polymer. So, this is reactive chlorine groups are there, the sulfone group and this sodium salt of bisphenol A in dimethyl sulfoxide solvent. If these reactants are heated, so this kind of polyether sulfone are formed. Again, this is a very good high performance, high temperature resistant polymer, or one can say again this is a multi-strand polymer or ladder type polymer, providing high thermostability as well as strength. Polyaryl ethers, this is actually aromatic groups, ether group, ketone group. So, the name of this polymer is polyether ketone. Thermoplastic polyamide. Now, we were discussing about the polyimides. Now, in one polymer backbone, one can have both imide as well as amide linkage, that is known as polyamide-imide. That gives a combination of properties of polyamides, say nylons, with the polyimides. Okay. So, this polyimide characteristics are developed in this polymer by reacting suitable monomers or reagents to form this polyamide-imide linkage. This is the imide linkage, this is the amide linkage. So, in a polymer backbone, if these two imide and amide linkages are there, that is known as polyamide-imide. This is a Tordlon, the trade name of this polymer is Tordlon. There are liquid crystal polymers. In other lectures, I have already developed the liquid crystalline polymers, discussed the liquid crystalline polymers, which are having ordered structures. These are actually mesophagic polymers. That means, in the liquid state, these polymers show crystalline order. Liquid state means in solution or in melt condition, they shows anisotropic behavior. So, this anisotropic behavior in liquid phase is known as liquid crystalline phase. So, this liquid crystalline phase that occurs due to rigid rod like configuration structures of the molecules. When such units are present in that polymer, those units are known as mesogens. If those mesogens are present, then that gives long range order in the liquid phase. So, in a polymer, so this kind of biphenol, this kind of biphenol, if that is reacted with say hydroxybenzoic acid, again that is also reacted with that is terephthalic acid. So, terephthalic acid, hydroxybenzoic acid, biphenol moiety, all these are linked in one molecule, and due to the presence of this phenyl ring, ester linkage, etc., that forms a long range or a rigid rod like configuration, and that is known as molecularly ordered liquid crystal polymers used as matrix resin for making high performance strong composites. This is a Zyder polymer, this is a vector polymer. Here this terephthalic acid, hydroxybenzoic acid and hydroxynaphthoic acid, these are there. Now, here you see the melting temperature or glass transition temperatures are varied from one polymer to the other polymer by selecting a suitable architectural unit. This is known as, one can say this is known as crankshaft unit. Here you see because of this kind of linkage, it decreases the melting temperature from this polymer. These are different types of liquid crystalline polymers. Now, let us look into the, till now we have discussed at length the different types of matrix resins polymers as the matrix continuous phase for making composites in both the thermoset and thermoplastic category. That is one component of the composite, and the other component of the composite is fiber, which is most important. And these fibers, what would be the characteristic of the fiber? The fiber must have high aspect ratio, means the aspect ratio is the ratio of the length of the fiber to diameter. That means, thinner the fiber, higher would be the aspect ratio. That means, higher would be the surface area of the fiber, and that will provide more interface area between the matrix and the fiber, and that can lead to a very strong composite. So, that is why if the aspect ratio is very high, and that will give very strong composites as they satisfy the desired conditions and transfer strength to the matrix constituents. So, this strength, transfer of strength as transfer of load, that will be maximum, that will be higher if the aspect ratio is very high, if the interface area is very high, and that influence and enhance the properties of the composite as is planned or as is desired for one particular grade of product. The performance of a fiber composite is judged by its length, shape, orientation, composition of the fibers and mechanical properties of the matrix regime. Composites may be fabricated with either continuous and short fibers. As you have seen, a composite may be made from particles. Today is the era of nanomaterials. If the reinforcement is of nano dimension, the composite we get is known as nano composite. For example, in the last lecture I referred the example of automobile tire, where carbon black was the fiber, was the filler reinforcing filler. The diameter of this carbon filler particles were around, say for example 30 nanometer. But the problem is with this 30 nanometer carbon black, even if the particle size is of 30 nanometer dimension, but they form by virtue of their high surface area, and since these are incorporated in a high viscosity polymer like rubber. So, these carbon particles form aggregates or agglomerates, aggregate. So, in the rubber matrix, these carbon black fillers are no longer nano filler that way, because they form the aggregates. Until and unless they are dispersed or broken to such dimension, that cannot be a nano filler. Anyway, by virtue of their chemical and physical characteristics, carbon fillers reinforce the carbon black fillers reinforce the properties of the rubber composite. That is why we get that very good strength performance of the tire. Now, in place of carbon filler, if somebody uses some other kind of nano filler like say malt MMT clay, malt morillonite clay modified with organic compound known as organically modified clay, having layer structures. Actually, this is sodium MMT, sodium molybdenite clay having layer structures in nanometer dimension. Such clays are such clay fillers MMT clays known as this organically modified clay known as cloisite. One grade is say suppose 30B organically modified clay. Only a 5 part of such clay in say rubber can provide huge strength properties, because if somebody calculates the surface area of this cloisite 30B would be as high as the surface area provided by 40 to 45 parts of carbon black used in 100 part of rubber. So, 100 part of rubber with 5 part of clay can reach the mechanical properties of this say tensile strength by using 45 parts of carbon black. So, one can get nano composites using nano fillers say clay or other nanoparticles say metal nanoparticles. If those are incorporated in a polymer matrix, one can get very good strong composite because of high surface area of the nanoparticles. So, here the performance of a fiber composite is judged by its length, shape, orientation, composition of the fibers and mechanical properties of the matrix region. So, if the surface area of the reinforcement is very high, the composite, the properties of the composite would be very high, strength properties would be very high. That will it can give very good synergism in properties, synergistic properties can be available. Now, let us look into the fibers, different types of fibers which will be suitable for making such composites. So, organic and inorganic fibers are used to reinforce composite materials. Almost all organic fibers have low density, good flexibility and elasticity. Inorganic fibers are of high modulus, high thermal stability and possess greater rigidity than organic fibers. And one can have diverse advantages of organic fibers which render the composites in which they are used. So, different types of fibers say glass fibers, E glass, S glass, A glass, R glass already I mentioned. Silicon carbide fibers, mostly one can say whiskers, silicon carbide whiskers which are actually single crystals of silicon carbide, that can lead to high performance composites. High silica and quartz fibers, alumina fibers, metal fibers and wires, graphite fibers, boron fibers, aramid fibers. Aramid fibers are basically aromatic nylon having this para linkage. This is the repeat unit of say aromatic nylon aramid. Aramid fiber is a very strong fiber, strong aromatic nylon fiber for making high performance composite. Natural fibers. Now, this is another area, natural fibers. cotton, jute, ramie, sisal, flax, and so many. These natural fibers with natural matrix resin can lead to green composites. These green composites are mean they are eco-friendly, fully biodegradable, as well as they are rigid and strong. A full automobile car body except engine, automobile car body except engine can be made from this green composite. After the life of the car, then that car can be disposed and nature itself will take care of its disposal and management by degrading it. So, it will not evolve any pollution to the environment. So, these green composites can be made from natural fibers. Out of these natural fibers, this ramie, sisal, flax and jute, they have shown a good promise for such composites. Now, for such green composites, this natural resin, natural matrix resin could be polylactic acid PLA, or one can take soy resin from soybean, soy seeds. There are commercial soy resins available in the name SPC, soy protein concentrate, or soy protein isolate. These are basically protein molecules having peptide linkage, vegetable protein. They are used as matrix resin, which are biodegradable and naturally occurring. Now, this soy resin SPC and SPI along with the sisal or ramie or flax have been found to yield very strong green composite, which is rigid, stiff, tough, but it is biodegradable. The resin is hydrophilic. So, if it is not exposed to humid atmosphere, or if it is not kept immersed in water, this resin can perform for longer period of time, but ultimately when it is disposed, it will degrade. So, this is the nature of the green composites. Thank you.